Today, I will be talking about this as Savannah introduced some machine learning methods for control problems games, and then with a particular focus on a recent framework we developed for the mean field games. So the talk will be have two parts. In the first part, I will give a very brief overview of the several learning methodologies that has emerged for control and games during the past, roughly speaking, the past decade. And then in the second part, I will focus on the new machine learning methods that we developed. Okay, so let me start. Okay, so this slide is just really a short motivation. So a modern decision-making system appears in many forms. For example, if you imagine there's a large investor try to allocate capital across a certain market, a financial market, or governments try to balance between the climate risk and also the economic growth, or some autonomous systems interacting strategically under partial informations. Okay, but despite of their differences, the system are having several common features. For example, the systems are usually having uncertainties, and then the decision makings are usually under partial informations, more model ambiguities, or the decision are usually has to be strategic. And then sometimes the systems are very high dimensions. So classical control problems and games theory, they provide elegant mathematical frameworks. For example, you have the AJB approach, the PD approach, or you have the maximum principle, which give you the forward-backward stochastic differential equations. But once the system doesn't give you a tractable solution, then the computation numerical methodologies becomes a tool to give you some ideas or some numerical solutions, but then the computation could become extremely challenging in complex systems, the traditional ones. So the natural question to ask here is that can the machine learning provide scalable tools for such systems? And over the roughly the last decade, several machine learning based methodologies has emerged for controls and games. So let me just begin with a very quick review here. Okay. So in this first part, I will briefly discussing three approaches. They are how to handle the stochastic control problem, how to handle the games, and how to handle the mean field systems using machine learning, or more specifically, the deep neural networks. And then in the second part, we will be focusing on recent machine learning methodologies for mean field game. Okay, so let me start. Let me begin with this classical control problem. So let's pin down the notations first. So we consider this control diffusion process driven by Brownian motion. B is euro the drift, sigma is the euro volatility. You have alpha to be the control process to choose, and the goal is to choose alpha such that you minimize the expected computational cost functional of the running cost f plus some terminal cost g. And then traditionally there are two main approaches. One is the dynamic programming principle. So if we are looking for Markovian control, which means your alpha is a function of the current state and then current time, then you can derive the Hamilton-Jacobian-Bellman equation. Or if you are generally looking for alpha to be a progressively matchable processes, then you can do the Pointryagin maximum principle that leads to a forward-backward system. Okay, but both are very mathematically powerful, but if you compute those system of equations directly using traditional methods, then the computation becomes very difficult in the high dimensional case. So this is so-called curse of dimensionality. So this motivates the development of the machine learning based methodologies that can use neural networks and then Monte Carlo simulations, and so that you can potentially avoid the spatial discretizations. Okay, so for those of you who try to have a first-hand or at the very beginning of entering this field, and then if you're interested in the approaches that was developed in the past decade, then let me have a small advertisement. So this is a survey that I wrote with Matthew Laurie, and then it summarized the very basic approaches for those type of problems, including the ones that I'm going to talk about today. Okay, so let me then briefly mention three representative methods. The first one is always direct policy learning. So we call this the direct parameterization. The main idea is just to parameterize the policy that you want to learn using some neural networks. And then instead of solving the value function or solving the FBSDs, then you directly update the parameters of this neural network using stochastic gradient descent. And the cost is approximated by the Monte Carlo simulations. Okay. And then there are two approaches in this directions. Either you do a global in time that was proposed by Han in 2016, almost it's exactly 1 decade ago. And then basically you have one unique neural networks to approximate the entire function relations. Or you do a local in time that was proposed by the second group later, and then each of the time there's a distinct neural network, and then you try to do dynamic programming. So you try to learn the optimal control at the second last time, and then you use that as the optimal one, and then you try to do the third last optimal control. Okay, so then this will encode the dynamic programming principle, and then you do it one by one. And of course, each approach usually have their own pros and cons. So the main advantage for both of them is that you can directly get access to the control policy, and then the coding is very, very simple. But then there are also some like disadvantages. For example, if you do global in time, you cannot really have many time intervals. So otherwise, you will have the vanishing gradient issue. And for the local in time, you don't have this because you are at every small step you are doing your optimization, but at the same time, because you are using the previously approximated solutions, you may accumulate the error. So there could be a potential propagation of error. And also for this type of numerical algorithm, the sampling complexity is usually high, and then the analysis is still under investigation. Okay. So the second one are really using the HJB approach, using the PDE. Basically, you do a dynamic programming principle. You rewrite the control problem into a partial differential equations. And here, due to the nature of the control, the problem itself is nonlinear. You have the infimum over all possible controls. And then almost at the same time, there are two groups proposing the basically the same idea. One is from the Justin Cipriano and Spilopoulos, and they call it to be the deep Galerkin method. And the other one group there from the Brown University, they call it to be the physics informed neural networks. But the idea are roughly speaking, very similar. They try to parameterize the solution of the PDE using a neural network, and then train this neural network by minimizing the following loss. So that this loss has two components. The first one is trying to force the neural network to satisfy the PDE relation. Okay, and the second one is try to force the neural network to satisfy the terminal condition. Okay, so then they update the neural network by doing the stochastic gradient descent for this loss. And then the methodology would avoid, again, the spatial grade discretization and potentially avoid the curse of dimensionality. Okay, and then there are some advantage for this one. So you don't have to do the sampling of the past, and then you can learn directly the value function. And then for certain type of the PDEs, you can perform error analysis. And this is because now you have the PDEs as the underlying equations that you want to solve. Then usually the PDE analysis can come in and play a role and tells you when you can stop your training. So basically the error analysis will tell you, okay, if my training error is at this low, then how would that relate to the difference between my approximate solution and the true solution? So that really give you a priori estimate on when you could stop your training. Okay, but there are also some potential room that people can improve. For example, if your PD is on an unbounded domain, then where do you need to sample your points so that you want to evaluate your loss, right? So where is the domain of your interest? And then in order to fully express this PDE residual, then you really rely on that alpha to have an explicit expression from your Hamiltonian. Okay, and then some of the problems that have this that have these features, then you need to there's other there's extension for these two methods which can handle that. Okay, and then there's the third methodology, which is based on the BSDs. So we can always formulate the control problem using BSDs with this nonlinear Feynman-Cake formula. Basically, that could relate the AJB equation with a backward stochastic differential equations. Or you can really go to the Monge maximum principle. Then this will give you a forward-backward stochastic differential equation, but then it will be coupled. And then based on solving the BSD or the FBSDs at the very beginning, when the machine learning emerges for solving stochastic control problem, there are two main approaches. The first one is called the BSD that was proposed in 2017. Basically, you simulate both the forward pass and backward pass in a forward manner, and you try to match the terminal condition of your simulated pass and then the terminal condition that's supposed to be satisfied by the BSD part. Okay, and then the DBDP. Well, the first one is also having this approach, having the feature to be trained in the globe manner, and then the second one is called DBDP, and this one it's also share a spirit that is called the local in time because you want to solve this backward stochastic differential equation in a backward manner. So you know what where to start as the terminal condition, and then you go one step back, and then you solve this y, and then you keep going back until you approach time zero. Okay. So then for these two, first of all, they share the pros and cons that I talked about for global in time, local in time, for direct parameterization method. And then there's additional advantages for the BSD method because here everything is simulated. And then you really visit the paths where, visit the areas where the system visit the most. Okay, so you have the training adapted to the past distribution. You do learn better where the system visits the most. Okay, and then for the second approaches, if you are doing, if you have a coupled forward-backward system, but due to the nature, then you have to guess the initial optimal control first, and then simulate the forward process, and then go to the backward. But this is not the thing that the DBSD method could need to vary. But for the DBSD method, if you are trying to relate the AJB equation to the nonlinear Feynman-Cake, usually you will have multiple choice for your f. And then how to choose a f such that the solution, the system is very stable or could give you accurate solution. Then this is also needs to be discussed in the literature. Okay, so then but basically, roughly speaking, those are the three mainstreamed methodologies for solving the control problems. And then we try to extend it to the games. So first of all, the player games, which means this basically says that you have a multiple strategic agents that interact through the dynamics and the rewards, and then how to find Nash equilibrium in high dimensions. So imagine if you already have a high dimensional control problem, now you have multiple agents that interact with each other, so the problem could be even high dimension. So back to 2020, I introduced a methodology, idea called deep fictitious display. Basically, this uses the deep learning tools plus the idea of fictitious display from economics. So basically, you let the idea is to iteratively do the best response learning. Each player repeatedly solve a stochastic control problem while treating the empirical behavior of other players as fixed. Then when they are solving the control problem repeatedly, then each of them are still high dimensional. This is where the previously introduced machine learning methods can play a role. So those high dimensional problems are tackled by deep learning methodologies. And then later on, there are many extensions on that. For example, if you have path-dependent features in the game, how do you do that? Or if you have non-local term, you have a Levy jumps you have jumps in your system, then things become the PDEs become non-local. Then how do you do that? So there are many extensions in this direction. And then when the number of players becomes larger and larger, then there are the mean field regime, right? Depending on whether the players are competing or cooperating, we can have the mean field game and the mean field control problems. And in particular, for the mean field game, there's an additional requirement, which is that you require the consistency between the optimal control and then the induced flow of the distributions. Okay, and then people also try to develop machine learning methods for the mean field game. So I will skip this part at this moment. When I talk about the second part, I will give some a list of literatures. But the main challenges for the mean field problem is so when there's additional thing that we need to learn, that is the distribution itself. This is a object living in the infinite dimensional space, then how would you approximate it accurately? Then this is not an easy problem. And then you have three things usually coupled together: the control, the value function, and the distribution. And in addition to that, if you have the common noise, then how would you handle that? Everything becomes more complicated. You have the conditional expectation, you have the conditional distribution, and then you have the value function, and then the Fouk-Planck equation both become stochastic. And even on top of that, when you are developing numerical methodologies or machine learning methodologies, how would you prove the stability or the convergence analysis where everything couples together? And then can that give you a guidance for your hyperparameter choices or the fine tuning of your learning parameters? Okay, so this is pretty much a review about the first part. So I hope there's no questions. And if not, then I will go to the second part, which is new methodologies that we developed for learning mean field game. And this is based on a joint work with Mo Zhou from UCLA, Hao Sheng Zhou from UC Santa Barbara. And then this is our archive number we posted last year. Okay. So let me pause here for 1 second. Is there any question?
I don't see any questions in the chat as yet.
Okay, good. So then let me go to the second part. So the idea for developing this learning scheme is to combine the idea of reinforcement learning and also optimal transport. Okay. So let me have a very short introduction for the reinforcement learning. So reinforcement learning, you already described the following scenario. So you have a interacting agent that with a unknown environment, and then you try to learn policy that maximize the reward or minimizing the cost, but you do not know the underlying environment. And then in reinforcement learning, there are many known developed methodologies. Actor-critic is one of them. So actor-critic will split the learning into two components. The critic will estimate the value function of the current policy. So it gives the feedback on how good the current policy is. And then the actor will try to update the policy using the feedback of the critic. So basically you have one thing to approximate your control and one thing to approximate your value function. So then our idea is trying to extend this structure to the mean field game, but also combining with the optimal transport idea. And as I mentioned in the past, for the mean field system, we must additionally learn how to involve the population distribution. Okay, so for our proposed framework, we call this MFAC. We combine the actor critic and also a distribution flow. Okay, so we are now the first one to work with the flow for designing machine learning algorithm, and eventually we can have the convergence analysis. We are following this work by Jianfeng Lu and Mo Zhou back to 2024, and then they are doing the class. They are proposing this methodology for the classical control problem, and then our contribution is to have this additional distribution flow that we updated from the continuity equation from the optimal transport, and then we are able to have the global exponential convergence under suitable time scales. Okay, so then to summarize, the main contribution is that how we handle the distribution flow and then how do we handle the convergence here. Okay. So let me start with pin down the notations for the mean field game. So if we fix a population measure mu, then consider a representative agent, then the dynamics will depend on its own state, the entire distribution, and also the control. And then the representative agent will try to choose a alpha such that his running expected cost function or it's minimized or expected reward are maximized. Okay, and then a mean field equilibrium is a pair of a alpha, the control and distribution, such that if I'm given the flow of measure to be mu star, then alpha star it indeed solve the optimal control problem if you replace the mu by mu star in the above system. And together, we have a consistent condition says that the marginal flow of the optimal state dynamics following mu star and alpha star has to be coincide with the given flow of measure. Okay, so the second condition also mimic the Nash equilibrium in the finite player case. That's no one has incentive to deviate from their control. Okay, so numerically, the challenges would be first of all the equals of dimensionality in the in the state space. So if you have X to be high dimension, then how do we handle it? And then the second one, which I think is more pronounced, is how to learn and represent the distribution in high dimensions. Okay, so then this is one of the central motivations for our mean field actor-critic flow. Okay. And then this is the one slide of literature as I promised from the first part. Mean field game has been introduced more than approximately like 2 decades, and then well known from the group from France and also the group from the Canadians. And then from after the introduction, there are many variants. For example, people talk about major minor, people talk about heterogeneous agents, stackable mean field game, finite state when there's only finite state, common noise, blah blah blah. Okay, and then from the numerical and learning part, the classical methodologies has been developed in the past for quite a long time, and I recommend this book by Axtell and Lauria in 2020. They have a very good summary for the traditional methodologies, how to discretize, for example, discretizing the PDEs and using PDE techniques to analyze the numerical error. And then for the deep learning part, there are also like 4 different approaches, whether you could do a direct parameterizations of your policies, or you try to solve the PDEs. That's the second part, second two references, and whether you try to solve the corresponding forward-backward stochastic differential equations, but now it becomes the Moquin-Belousov type, or recently there's papers on how to solve the master equations corresponding to the mean field game. And all of the above 2 bullets, they assume that we know the systems, and nowadays there's also model-free mean field games, which means you have even one agent interacting with infinitely many other of them, but nobody knows the exact environment, and then how to develop the model-free methodologies using the idea of reinforcement learning. And there's also a bunch of literatures along this line. And I do apologize if I miss anything. This is by no means a exhaustive literature list. Okay. So let me quickly skip this. So then before I introduce our methodologies, let me fix some notation first. So because for our case, we parameterize both the actor and the critic. So this critic will be based on a particular control and a particular distribution. So we will just we only care about the this value function that follows this we are not varying the control, so we are not optimizing the control for this value function. You just give a control and give the distribution, then this V will satisfy a linear PDE. Okay, so the linear PDE will play an important role in the analysis later on. Okay, but we do not solve this PDE directly. Okay, so how do we then learn the this V or this we call this critique in the machine learning? So we use this shooting method. Okay, so the way to learn the critique or to learn the value function along a given distribution and along a control is we parameterize both the value function at the initial time and then the gradient of the value function using neural networks. So those curly graphic letters are the neural network counterparts of the thing that we want to approximate. And then we update those V0 and G by minimizing this loss functional. Okay, so this loss functional, the idea is inspired by just the stochastic representation obtained from the Ito formula. So if you do Ito formula to this process, then you will naturally have this. So then for the true value function at time zero and the gradient of the value function, you naturally have this identity. And then we hope that the neural network counterpart will also satisfy this in some sense, in the L2 sense. Okay, so or you can also say we compare the loss, the critic loss will compare the terminal payoff with the stochastic representation governed by a learned control. Okay. And then once we design our loss functional to be in this way, then there's a natural orthogonal decomposition. So essentially the loss for the critique will measure the loss, will measure the error from the neural network counterpart of the initial value function and the derivatives weighted by the weighted by the state density. So we're able to rewrite this L2 loss into this case, where rho zero is the initial distribution of the mean field, and then rho mu alpha is the distribution if the state dynamics follows the control alpha, and then the current distribution plugged in is mu. Okay, and then the update will just rely on, although we have this, but the update will just rely on simulate the trajectory of your x and then evaluating loss using Monte Carlo simulations, and then try to do gradient descent with respect to the neural network parameters, which are brought by the G and the V0. However, if we look at if we try to take functional derivative and then look at how things are updated in theory, then we will see that the direction for the update is exactly towards to the true solution. Okay, so those two equations will be very useful for analyzing the convergence, but not for the numerical algorithm implementations. Okay, and then the key point here is that when we do the update numerically, we never compute these two terms numerically. Okay, so as I mentioned, the things are evaluated using Monte Carlo and then simulating the trajectory, but those two are the essential equations for analyzing the convergence. Okay, and then the notations we introduce are given below. So this is the how we define the functional derivative. Okay. And then for the actor, this is not something we introduced in our paper. So we follow this previous theorem from Zhou and Lu back to 2025 in the SIAM paper. So they derived the functional derivative of the cost of with respect to the control. And for us, we do not have the control in the diffusion case, so we can drop the second derivative. Okay, and then we also approximate the gradient using neural networks. So in that case, the update on the actor will be given by the right-hand side. Okay, so it really depends on the critic's estimate brought by this curly graphic G. Okay. Okay. So now let me talk about how do we update the distribution. This is I would say one of our main contribution, or this is the new ingredient that we brought into this framework. So we know that in the classic mean field game, there's one way to construct the mean field equilibrium, which is by fictitious play that was introduced by Cadillac and his co-authors back to 2017. Okay, so the main idea is that one iteratively update the population distribution using the best response. Okay, and our idea is try to replace these discrete iterations by a continuous time learning flow. Okay, so in the rest of the talk, I will introduce a new notation, tau. So tau is the time the learning time. Like if tau are integers, that means at iteration 1, 2, 3, 4, 5, then how the state system looks like. But now tau is a continuous time, then we are able to, in this case, we are able to have a better convergence analysis. And I want to differentiate this tau parameter with t, where t is the physical time in the mean field game. So t is it's a real number from 0 to capital T because we are dealing with finite horizon mean field game, but this tau can goes from 0 to infinity and also a real number. Okay, so what do we mean by this optimal transport geodesic Picard flow? Okay, so then it's just at each learning time tau, we look at the current distribution, or current estimate of our distribution, and the current estimate of the control, and then we try to move this distribution towards the one-step best response distribution along the Wasserstein geodesic. Okay, so the one step response is you just plug in mu tau and alpha tau to the SD that we showed at the very beginning of the part 2, and then you look at the resulting distribution of that XT. Okay, and then this movement can be characterized by this continuity equation, where this phi is just the convergence potential for the quadratic cost of this form. Okay, and then we want to emphasize that because the target that your mu tau is trying to chase another target which is called the rho mu and alpha, and because your mu tau when tau is moving, your mu tau is moving, but your target is also moving. So this is not a classical a standard Wasserstein gradient flow. For a standard Wasserstein gradient flow, then your target is really fixed, and then you try to compute how do you optimally move one distribution to the target distribution, right? But now your target distribution is also moving, so then in this case, the optimal transport geodesic Picard iteration is not a standard Wasserstein gradient flow. Okay, and then so this will serve as the baseline for our analysis on how the flow is or how the distribution is updated. But in practice, when we are doing the update, we do not parameterize the distribution and using neural network. And because if you are parameterizing the distribution, then there's always a normalizing constant that you need to you need to figure out, but this is usually very hard if you're using a neural network to parameterize a function, right? So it's not easy to guarantee that the neural network that you use to parameterize a distribution indeed give you that the integral is 1. Okay, and then the way that we handle it is that we try to use a score function to approximate this density. And then we use score matching to update the distribution, and then we try to use Langevin dynamics to recover the distribution from the score function, and then we compute the optimal transport map using Hungarian algorithm. Okay, I will discuss more for the next step. But basically after this 3 step, this close the one iteration of the update. So we update the critic using the shooting method, and then we update the actor using a Priestley policy gradient, one type of policy gradient theorem, and we update the distribution using the a continuity equation. And then, of course, you want to update them at different speed such that we can have a nice global convergence. So then we multiply the right-hand side by different parameters, beta c and beta a and beta mu that represents the convergence, that represents the speed of the updates for critic, for actor, and for distribution. And then later on, we are able to show that under the scale that your controls update is relatively faster than the update of the actor and relatively faster than the update of the distribution, then we are able to have a nice convergence results. Okay, so this is the part for the design of the algorithm. The next slide, I will move to the proof. Okay. Any question? Okay. So at this point, we have three coupled learning components. So the critic will depend on the current policy and the current distribution. The actor will use the critic's estimate to improve the policy. And then the mean field also involved under the current policy. So the three things are strongly coupled. So as I mentioned, the one key to stabilizing the mechanism is to do this time scale separations. So then we need to analyze how the three parameters are chosen. But first of all, we want to introduce a Lyapunov functional, and then that will help identifying the three scales. So this Lyapunov functional will have three components: the one part from for the actor, one from the critic, and also one from the distribution. Okay, so the one from the actor measures the actor's suboptimality. So under the current distribution, how far is my current control from the optimal control under the current distribution? Okay, and the critique will measure the approximation error. This is basically a similar version of the critic loss that we introduced before. And then the Lyapunov functional for the distribution will try to characterize the distribution mismatch. So how far is our mu tau from the one step best response, rho mu tau alpha tau. Okay. And then we are trying to do estimate for each of the component. So the key estimate here is that each of them will have a dominating negative term or dissipative term. Those are highlighted in blue. So those are good terms. So we want those good terms, and then they also have the red terms, which are the small coupling terms generated by the other flows, and those are the bad ones. So essentially, or ultimately, we want the blue terms to dominate the red terms, so that in the end, you have the sum of the derivatives to be less than or equal to the sum constant multiplied by the sum. Therefore, you will have a global decay. You will have a global convergence. Okay. So the first one, let me just try to explain some of the terms. So here, for the actor's Lyapunov functional, you have two good terms. So this one will stay. And then the second one is trying to compensate the bad terms that are from the Lyapunov functional from the critic and also the Lyapunov functional from the distribution. So this actor coupling and then this actor coupling is essentially the same term as this one. Okay. And then by carefully choosing my beta A and beta C and beta mu, I will be able to have this coefficient to be bigger than this one and this one. Therefore, you can use this term to dominate these two red terms. Okay. And let me see. These terms you don't need to worry too much because this term can be covered by this one by carefully choosing beta A, the relation between beta A and beta mu. Okay, and this term is actually determines our form for the Lyapunov functional of the distribution. Okay, so our Lyapunov functional for distribution will not only measure the distance between mu tau and rho mu tau on the entire time from 0 to capital T, but there's an additional term that only measures the distance at terminal T. So if we are just trying to have the convergence Well, if we are just trying to say that this indeed give us a mean field equilibrium, then we don't have to have the second term. As long as this term converts to zero, then we already obtain what we want. But because this term appears in the estimate of my Lyapunov functional decay for the critic, so I have to add this term to the construction of my Lyapunov functional for the distribution. Okay, but ultimately, by carefully choosing the three parameters beta A, beta mu, and beta C, we are able to use this term to cover the rest of them. Okay, and then the big theorem for the convergence analysis will look like the following. So we do have a lot of assumptions for the dynamics and for the learned trained neural networks, and also on the separation of the time scales. Okay, and after all the things are satisfied, then we are able to show that the flow, the mean field actor-critic flow will satisfy this. So the decay of my Lyapunov functional is upper bounded by the negative linear of my Lyapunov functional. So equivalently, that means there's an exponential decay, and if I run this dynamics infinite long time, then the distance between all the three Lyapunov functional will converge to zero. And this means simultaneously the population law will go towards to the mean field consistent condition, and then my actor will be the optimal response under the mean field mu star. So the first one, the convergence of the Lyapunov functional for the distribution will identify that we indeed find a mu star. And then the convergence of my Lyapunov functional for the control to zero will identify that we obtain the optimal response alpha star. And the Lyapunov functional for the critique goes to zero will tell us that we learned the value function and its gradient associated with these two alpha star and mu star is also accurate. Okay, so I hope this is not too abstract, but if there's more time, we can talk maybe more about this, the proof here. Okay, but the basic idea is that for each of the estimate, there's one or two main dominating terms that help with the decay, and there are smaller bad terms that is due to the coupling with other components, but we are able to handle them by using the negative good terms. Okay. So then it's about the implementation part. The actor and the critic are very standard as implemented in the previous work. And let me just have one slide illustrating the implementation of the distribution. So I think this is also one key contribution in the implementation part, which is we use the score net we use a score function to represent a distribution, which is the score is the gradient of the log of a density. In this case, you avoid evaluating the normalizing constant that from the any function, in particular from your neural network approximation. Okay, but then you cannot really go from the score function back to the density. So how do you recover a distribution? You do sampling. You sample through the Langevin dynamics, where the drift it takes the form of your score function, and then you are using those samples to represent your distribution. Okay, and then once you have this distribution, you can sample the forward dynamics to construct the samples of the best response law. And then you can compute the optimal transport map. And in here, we are using the Hungarian algorithm. And this is an exact algorithm, and the complexity depends on the number of the samples. Or you can also use Sinking-Korn form algorithm if you would like. And then we are able to compute the optimal transport samples after we compute the transport map. Here, eta is the after you do the discretization, how much you move from one step to another one. And then this serves as the new samples for you to update your new distribution. And here we are using the score matching. Score matching is a very popular method nowadays that people are using also in generative models. that was introduced back to 2025 at the paper by JMLR. Okay, so I would say here three ingredients for this implementation. The first one is you try to use the score function to represent the distribution, and then you use Langevin dynamics to recover the distribution from the score dynamics, and then that's the first component. The second one is how do you compute the optimal transport map, and the last one is how do you do the update, which is by the score matching method. Okay. And then in the last maybe 3 to 5 minutes, how much time do I have, Savina? Maybe 3 to 5.
About 5 minutes, yeah.
Okay, good. That's perfect. So I will talk about two examples. So the first one is this very well-known systemic risk examples. And then the reason we choose it is because it has a explicit solutions. So we can nicely benchmark everything. And this is a quadratic problem. And so we have two sets of plots. The first one is you see the this is on the top. This is the comparison between my gradient approximated gradient of the value function and the value function itself. The blue lines are the benchmark solutions, and then the red ones are our approximated results. And then you can see that they align on each other pretty well, except for the last one. And here there's some mismatch, but I want to mention that under the histogram, which is the place that the dynamics visit the most, or this is the distribution for the optimal state variables. And then we do not really visit the regions outside of here. Therefore, it's okay that if we learn this part not as accurate as enough because we never use the learned functions there. Or it makes sense that we didn't learn it well because we didn't visit there a lot, right? And then the bottom panel plots the comparison between the optimal control and its approximations, and they are also very aligned with each other. Okay. And also, if we look at the histogram, the dashed lines are the benchmark solutions. And so they are the truths. You have a Gaussian distribution because everything is linear quadratic. And then this histogram plot in Crane, it's the samples of my forward dynamics under the current learned policy and current learned distribution. Okay, and then you can also see they match with each other pretty much pretty well. Okay. The next plot try to examine the estimate of the distribution from another one. So we also try to learn the score of the density using score matching. And then for here, the red line is computed using the Langevin dynamics when you are having the score as the drift of your Langevin SD. And then again, the dashed line in blue is the true distribution from the benchmark from the example, and then they still get very aligned with each other. And the last one is the initial the value function at the initial point, and again at the locations where under the regions that the distribution with the most, then the value function at the time 0, they're aligned with each other. Yeah, there's a slightly mismatch at the very end. Yeah, because we didn't visit much on these two areas. Okay. And then this plot is trying to show the to validate the exponential decay as predicted by the theory. So you do see that at the very beginning, the decay is like linear because we are doing the log plot. Okay, and then after that, somehow the decay are slower, and this is we believe this is due to many other error introduced in the numerical implementations, like the discretizations in time, the sampling, etc., which are not included in the analysis of the algorithm's convergence. Okay, and then we do have a high dimensional example. So this is a 6-dimensional example for the flocking problem. So you imagine you have like a birds, and then the S describe their locations or positions, and then the V is their velocity, and then the birds, each of them try to choose their acceleration U such that their positions and their velocities are aligned with the entire distribution. So this problem is really a distribution dependent, and it depends on the entire distribution whenever beta is not zero. Okay. And then, so for this one, we do not have a benchmark solution. We do not have an analytical solution for a non-zero beta, but then there's a relative benchmark solution that from my previous work with Jie Han and Ji Haolong back to 2024. So we take that as a benchmark solutions that we want to compare. And then basically you can see the histogram of the densities from the state, from the positions and from the velocities are very aligned with each other. The purple ones are from the previous papers, and then the red ones are from these mean-field actor-critic samples. Okay, so so I think let me just stop here. This is another plot that's try to compare their distribution. It's very high dimensional, so we just compare each of the dimension one by one, not the multi-dimensional case. And then here are some references for the second part. And I would like to stop here and thank you for your attention. Thanks.
Thank you very much, Ruimeng. We have a couple of questions in the chat, and I can read them to you. I think that might be kind of easier. And if there's any more questions, please feel free to ask or raise your hand. So we have one it's about the convergence that you were just talking about. So it says that your convergence result is global but exponential. Is the rate dimension independent, or does it degrade with the sample state dimension?
You mean this one? I think this is free of the dimension. Yeah.
Free of the dimension. Okay.
Yeah, this could be free of dimension. Yeah.
Yeah, and then there was another question on how do you choose your betas in slide 23.
In this one, right?
Yeah,
So
exactly.
there's a complicated relations. So that so basically you want to choose your beta such that this term will be able to kill this term and this term. So you do see that you want to, for example, in the proof, we split this 1/2 beta 2, beta alpha to be 1/4 and 1/4, and the 1/4 of them will dominate this one, and the other 1/4 of them will dominate this one. So that will naturally create a ratio between the beta A and beta C. Yeah.
So you don't have to specify them
There's
a
a
priori.
there is a relation between the two, or there's a so as long as the ratio is less than something, then that should be fine. Or
But the
is the
ratio you can
question?
actually specify, like
Yeah,
quantify.
yeah,
Oh,
I can
okay,
quantify.
nice.
Yeah. But I'm not sure if they talk about numerical implementations, how do we choose it, or in the proof, how do we choose it?
It doesn't say. So how do you do it in the numerics?
How do I do in the numerics? For numerics, then we still follow the regime that we want to have these relations. Yeah. But then everything involves discretization also in time. So we still need a little bit of the fine tuning. Yeah. But the relation that we obtain from the convergence analysis can provide some guidelines there for the choice for numerical part. Yeah.
Okay, there's another question on in your mean field actor critic flow, how do you handle the coupling between the policy update and the population distribution update without introducing bias?
Can you say the question one more time?
Sure. Yeah.
Or which one is it? Maybe I can read from the Q&A part.
Yes, let me see. This is the second to last one.
Oh, okay. So in the method actor critic flow, how do we handle the coupling between the policy update You mean how to handle the update between this one and the this one, so that there's no without introducing the bias. I'm not exactly sure what does he mean by introducing the bias. So when you update the population distribution, it relies on the current estimate on the policy. And because the current policy is not the optimal one, then you do have some error made there. And that's why when we do the analysis, then there's the coupling term. So this is exactly the terms that you have it here. Okay. So your actor not learning the optimal one does influence the update of the distribution. Yeah. And then will decrease the performance of the update of the distribution a little bit. Yeah. Yeah, but we are able to in the long run, we are able to kill that part by running the algorithm sufficiently long. Yeah.
Okay, there's another question that just came in. So in the systemic risk example that you had, is there a way to mitigate the deviation in the tail part, especially in situation where learning in the tail part may still be important?
Yeah, you can do that. You mean this part, right? So you I think you can do some like randomized sampling techniques. So not exactly sampling the optimal or currently learned control policy and currently learned distribution. So basically, every time you need to sample from this dynamics from here. So every time for your numerical algorithm, you need to sample from this dynamics, and then with the current estimate of your mu and current estimate of alpha. And if you are really following that, then eventually you're only sampling at the regions where your distribution covered the most. But if you have some other techniques for your alpha, then you should be able to visit other areas, like doing some randomized control thing like that. And this is a very classical methodology in reinforcement learning that you maintain two actors. One is for training to approaching the optimal one, and the other one is just for sampling or for exploration. So in that case, you do not like stuck into some like local minimum or maximum points. Yeah, so that's doable. Yeah, that's a very good question. Yeah.
Nice. And then maybe if you could comment a little bit on the sample complexity of your mean field
11
actor
o'clock.
critic flow. In particular, how many trajectories do you need of your agents system?
The sampling complexity.
Okay.
I mean, for this part, right? So to be honest, we didn't analyze any errors regarding to the sampling part or time discretization part. And I would say it will depends on the it will definitely depends on the dimension of the state. If we are trying to that would be brought by the Wasserstein distance between the sampling empirical distribution and the true distribution. So yeah, but we don't have I don't have the exact answer here. What is the sampling complexity here? Yeah, sorry about that part. Yeah, but that will be dimension dependent. Yeah.
Yeah, there's one last question that came in just right now. Maybe we can have this as a final question. What about the diffusion coefficient and minimization functional that involves the control? Okay, I'm not quite sure I understand the question, to be honest.
I guess.
Oh, so what about if the diffusion coefficient and the minimization functional involves the control itself? I think that's the question.
I can understand the first part. So if sigma depends on the control, then the policy gradient theorem will be different. Or the policy gradient theorem, we cannot simplify that. But we need to, so the policy gradient theorem takes into account the second derivative when that means in principle, we can deal with the diffusion coefficient depends on the control, but then we also need a good estimate of the second derivative using neural networks. This could either be done by taking auto differentiation on the G part or use another neural network to approximate the second order derivative. But then this will introduce another component in the loss of the critic. But then the analysis will be much harder, much involved. And at this moment, to be honest, I don't know whether we can do that part. And the second question, I'm not fully understand what if the minimization functional involves control. So here our F does involve the control. So this is not a problem. So F can depend on the control. That's fine. Yeah.
Okay. Well, thank you very much, Ruimeng, for this interesting talk. And
Thank you.
yeah, answering all the questions. Thanks, everyone.